Circles and Arcs by me, Mr. Pi, the math guy. And you're going to see here in this lesson, we're actually going to be using pi since we're working with circles. So let's get this geometry party started. Here we have some information related to circles, some basic terminology, and if you don't understand this or know this, you should take a moment or a few moments to study over it or even write it down. In a plane, a circle is the set of all points equidistant from a given point called the center. A circle is named by its center. Circle A is shown. So from that, we can see here the center of the circle is going to be this point A. Here, blank, a segment has one endpoint at the center and the other endpoint on the circle. In this case, we're talking about this here. A to Z, and that's called a radius. And hopefully you knew that. Congruent circles have congruent radii. That'd be the way to say that. Radii, that'd be with two eyes. So congruent circles have congruent radii. Blank. A segment that has one endpoint on the circle goes through the center and the other endpoint is on the other side of the circle. In that case, we're talking about this segment here. We're talking about segment XY. It's on one side of the circle, goes through the center to the other side, and that's called a diameter. It's good to note that a diameter is made up of two radii, if you will. So we can multiply the length of a radius by 2 to find the length of the diameter, and we can take the diameter and divide it by 2 to find the length of a radius. Finally here, a central angle A central angle's vertex is at the center of a circle. So here we have a couple central angles. We could have angle XAZ right in here. That could be a central angle. We could have angle YAZ. That could be a central angle. So some review of basic parts of a circle. Here we have a problem-solving situation. Example 1T. A researcher surveyed 2,000 members of a club to find their ages. The graph shows the survey results. Find the measure of each central angle in the circle graph. Well, first thing you should know is in a circle there are 360 degrees. So what this boils down to is a basic percent problem. We know that 25% of the members here in blue, the 15 to 16-year-olds, were 25%. So we have a basic percent problem. So let's check that out. That'd be 25% of 360 degrees. When we do that math, and the way you would plug that in your calculator would be this. It'd be 0.25 times 360. When you do that, you should know that 25% of a circle is 90 degrees. That'd be a right angle. So the 15 to 16-year-olds are a 90-degree angle. So there's one of our answers. Now, as we move on to the 13 to 14-year-olds in green, they represent 40% of this group. So that would be 40% of 360, or 0.4 times 360. When you do 0.4 times 360, that gives you 144 degrees. So in here we have 144 degrees. I guess I should put that in here in blue. That this is a 90-degree angle. And we can mark that as 90, like that. Or we could have wrote 90 in there. So anyway, moving on to the 11 to 12-year-old group. The 11 to 12-year-old group is 27% of the members of the club. So we'd go 0.27, 27% of 360 degrees. This amounts to really some calculator work. When you do 0.27 times 360, that gives you exactly 97.2. And we could round that and say that's approximately equal to 97 degrees. So in here that'd be 97 degrees. And then finally, we could either add those up and subtract from 360, or we could just do, for the 8% here, the 9 to 10-year-olds, we could do 0.08 times 360. And when you do that, that comes out to be 28.8. And when you round that, that becomes 29. So in here, you'd have 29 degrees. And to check your work, you just go back and add these values up, and you'll see that they will add up to 360 degrees. Before we talk about arcs and doing any work with arcs, it'd be good to understand and discuss what the different kinds of arcs are. An arc is a part of a circle. One type of arc, a semicircle, is a half of a circle. So here in this diagram, we have a semicircle. We have AC, segment AC, acting as the diameter, and so then we'd have arc ABC is a semicircle. And since arc ABC is a semicircle, what we can conclude then is that the measure is 180 degrees, because the measure of a semicircle is 180 degrees. So the measure of arc ABC is equal to 180 degrees. Here we're told that the minor arc, or a minor arc, is smaller than a semicircle. In my second diagram here, I have a minor arc BC. The semicircle would be ABC, or arc ABC, and in this case, since arc BC is less than a semicircle, or smaller than a semicircle, we have a minor arc. So we could write this down as arc BC is a minor arc. And since arc BC is a minor arc, the measure of the minor arc is the measure of its corresponding central angle. So the measure of arc BC from here to here along the outside or the circumference of a circle is equal to the measure of this angle here. So the measure of arc BC is equal to the measure of angle BXC. And notice the start and end point of the arc is the start and end point of the angles. The third thing, in my third diagram, we're going to talk about a major arc. The measure, it says here, a major arc is greater than a semicircle. So here we could have arc BAC from here through A along the outside of the circle to C. So arc BAC, and we call that a major arc. So arc BAC is a major arc. And we define the measure of a major arc right here. The measure of a major arc is 360 minus the measure of its related minor arc. So the measure of arc BAC is going to be equal to 360, and that'd be 360 degrees minus its related minor arc. And in this case, the related minor arc is BC. So major arc BAC, so related minor arc is arc BC. So minus the measure of arc BC. And there's a little bit about major arcs, minor arcs, and semicircles. In example 2T, we're asked to do something pretty basic. We're asked to identify the minor arcs, the major arcs, and the semicircles in circle P with A as an endpoint. Now, this specification that A is an endpoint means it can be a starting point or an endpoint when it comes to talking about arcs. So let's talk about the minor arcs first. Now, the minor arcs starting from point A would be one of them going clockwise, would be arc AD. Now, turning that around, DA would also be an arc. So we'd have arc DA or arc AD. Two different ways to name the same thing. Now, going counterclockwise, starting with point A, we travel to point E. So that would give us arc AE. And switching those 2 points around, we could also call it arc EA. So we can see here, just by switching the order of the points, the endpoints or the starting and the endpoints, you can name minor arc two different ways. Now moving on to the major arcs. Now notice, major arcs, or remember, major arcs are greater than a semicircle. Remember, or we could see here when I did AD, minor arc AD, it was less than a semicircle. So starting with point A, if I travel clockwise to point E, which would be a major arc. Now I got kind of sloppy there and I apologize for that, but I'm not used to working with circles. Let me move that in a little bit, so that's good. But from point A to point E, we can name that major arc two different ways. And the way I really would name it personally would be arc ADE. Now you could name that, instead of ADE, you could name that ABE. Anywhere you see a D here, you could really replace it with a B. Now, again, if A is the start point, we go through over here to E, we have ADE. If we switch that A and E around, we can make it arc EDA. So arc EDA. So there's two different ways to name the same arc. Now the other major arc would be gotten by going the other way. That would be starting at A and going counterclockwise to D. Starting at A and going counterclockwise all the way around the circle to point D. We could call that arc AED. Here I use E as my middle point, not B, but E. So here we could replace E with B. And switching the endpoints around, we could have arc D, E, A. So there's identifying the major and the minor arcs. Now, identifying the semicircles, now that's pretty easy. Finally, we get to the semicircles. That's half a circle. So semicircle starting in A going this way, clockwise, A, D, B. So we'd have semicircle represented by arc A, D, B. Switching the B and A around, we'd have B, D, A. Starting in A and going counterclockwise, we'd have semicircle A, E, B, or arc A, E, B. Switching the endpoints around, we'd have arc B, E, A. So here, just identifying arcs, whether they be minor or major, and semicircles. It all has to do with your endpoint and which way you go around the circle. Welcome to this idea of the arc addition postulate. Now, to understand the arc addition postulate, you really have to understand what adjacent arcs are. Adjacent arcs are arcs of the same circle that have exactly one point in common. That point they have in common would be an endpoint. It'd be an endpoint of both arcs. The arc addition postulate reads, the measures of the arc formed by two adjacent arcs is the sum of the measures of the two arcs. So here we have a circle. We have circle, whatever you want to call it, doesn't even have a middle, but it would be, we could call it circle A. Here we have circle A, and in circle A we have arc XY, and we have arc XYZ, and we have arc YZ. Now what you need to understand is from X to Y, and then from Y to Z along the outside of the circle, is just like the segment addition postulate. If we go from X to Y, and then from Y to Z, we know the distance from X to Z through Y. This really has to do with a part plus part equals whole relationship. The whole distance, in this case, the measure of arc XYZ, is equal to the measure of arc XY plus the measure of arc YZ. The distance from X to Y plus the distance from Y to Z gives us the distance from X to Z through Y. And that's the important thing there, that we want to know the distance along the outside or along the circumference of the circle. So the arc addition postulate, just like the segment addition postulate and even the angle addition postulate, we're going to see how to use this to solve some problems. In example 3t, we're asked to find the measure of arc XY and the measure of arc dmx in circle C. So let's get over here and maybe let's highlight a little bit of what we have to actually find here. So in this case, we need to find the measure of arc xy. So that'd be the measure of this from here, x and y. So x through D to y. So we need to find that first. So let's go ahead and do that because we have enough information to do that. The measure of arc xy using the arc addition postulate is going to be equal to the measure of arc xd plus the measure of arc dy. Now we know both of those, so this is a really easy thing to do. So you might even be able to do this without using the arc addition postulate, but it might be good practice to write down the arc addition postulate, at least like this. So the measure of arc xd is 56, and the measure of arc dy is equal to 40. So we substitute those in. When we substitute those in, we simply add them together. 56 plus 40 is 96. So the measure of arc xy is 96 degrees. Next, we have to find the measure of arc dxm. So that would be here, dxm. So that's a pretty easy thing to do. You have to understand that arc xwm is a semicircle. Segment xm is a diameter, therefore arc xwm is a semicircle. So the measure of arc dxm is equal to the measure of arc dx plus the measure of arc xwm. When we substitute in what we know the measure of arc dx is 56 degrees because that's the measure of its corresponding central angle, plus the measure of arc xwm, 180 degrees because it's a semicircle. When we add those two together, 6 plus 0 is 6, 5 plus 8 is 23, or is 13, and I carry the 1, and then 1 plus 1 is 2. So the measure of arc dxm is 236 degrees. Here we're going to talk about the circumference of a circle. The circumference of a circle is the distance around the circle. It's another word for the perimeter of a circle. The number pi, Mr. Pi the math guy, is the ratio of the circumference to its diameter. So pi is a ratio. It's an irrational number. We can use 3.14. We could use 22/7 to approximate it, or on your calculator you can just use the pi key. Sometimes it's in the second functions. So here we have a theorem, really is a formula, the circumference of a circle. The circumference of a circle is pi times the diameter. And we can see here, little diagram, the circumference, the distance around the outside of a circle. Here we have a diameter and we have a radius. Now because two radii make one diameter, if we multiply 2 times the length of a radius, it'll give us the diameter. So instead of having just one formula, we do have 2. But we can always get one formula from the other formula. If we forget that relationship, the 2 radius or 1 diameter, then we can just memorize 2 equations. Circles that lie in the same plane have the same center are concentric circles. So circles that lie in the same plane and share the same center, they're what we call concentric circles. And we're going to see that in this upcoming example, how to solve a problem using concentric circles. Example 4t, we have a problem-solving situation in which we're going to use Rhys method to solving problems. Rhys stands for read, illustrate, solve, and explain. So let's get into reading our problem. A circular swimming pool with a diameter 16 feet will be enclosed in a circular fence 4 feet from the pool. What length of fencing material was needed? Round your answer to the next whole number. So when we read, what I like to do is write down important information. And the first piece of important information here for me in the read is that the pool has a 16-foot diameter. So I write that down. And I also know that the fence is going to be 4 feet away, so 4 feet away will be the fence. And I'm going to add to this the circular fence. Now, I'm going to write down my question. What length of fencing material is needed? Round the answer to the next whole number. So, how much fence is needed? Now you can see I have my diagram already set up. I hope that you'd be able to write this problem or read this problem and illustrate this on your own. But for the sake of video time, we're going to have it preset for us. Now we can see here I have the pole here in blue and its diameter is 16 foot. Now 4 feet away from that is the circular fence. What we have to calculate is how much fence we need all the way around, and what that amounts to be is a circumference problem. The circumference of a circle. Circumference is equal to the diameter times pi. Well, I have to calculate the diameter from one side of the fence to the other, and this really ends up being a part plus part equals whole relationship. We have 3 parts. We have the part plus part is equal to whole relationship, where we have 4 plus 16 plus 4, and that'll be equal to the whole, or the diameter of the fencing. And when we add that together, the diameter is equal to 24. A lot of kids make the mistake of saying that the diameter is going to be 20. They just go 16 plus 4. No, it's 16 plus 4 plus 4, or the way I wrote it, 4 plus 16 plus 4. It's a part plus part plus part is equal to whole relationship. In this case, the whole is the diameter. So now that I have all the information, I can solve. I can take the circumference. Circumference is equal to the diameter times pi. And in this case, the diameter is equal to 24 feet. And I need to multiply that by pi. Now you have 3 options. You can multiply it by pi on the calculator, you can multiply it by 3.14, or you can multiply it by 23 over 7. Now the pi button on the calculator I believe is the most accurate. So when I did my calculation, it came out to be 75.3982. Now that's going to round because it wants to the next whole number. So this is 75.3. So the next whole number is going to be 76 feet. So this is going to be approximately equal to 76 feet of fencing. And there, I really messed that up. We'll just scratch it out. 76 feet of fencing. And so we'll get into the explain portion here in a second. The explain portion, you can see I've typed it up here. It says I have to find the circumference of the circle created by the fence. The diameter of the circle is 24 feet. This circle is referring back to the circle created by the fence. Multiplying 24 feet with the pi button my calculator gave 75.3983 feet. I rounded this up because the problem asked for the next whole number. One thing that I didn't type in there is that the actual amount of fencing should be 76 feet. So I'm going to just finish that up saying fencing needed, 76 feet. So there's using Rhys to solve a problem. The measure of an arc is in degrees, while the arc length is a fraction of a circle circumference. And that's what's important about this slide. So we're going to be learning how to calculate the arc length here. The length of an arc of a circle is the product of that ratio, the measure of the arc to 360, and the circumference of the circle. So the measure of arc AB in this diagram is going to be equal to the measure of this arc in degrees over 360 times 2 times pi times r, the radius. This is the circumference formula. So we multiply the fraction of the circle that we're calculating in degrees, and we multiply that by the circumference formula. We're going to see an example of this coming up next. In example 5, we're asked to find the length of arc ADB in circle M in terms of pi. So let's get this one going. To find the length of arc ADB, we're going to have to find the measure of our angle AMB, or the measure of arc ADB. Doesn't really matter either way. The measure of arc ADB we're going to find by subtracting from 150 from 360. The reason we can do that is because arc AB is arc ADB's related minor arc, and those together make a full circle. And in this case, that would give us 210. So the measure of arc ADB is 210 degrees. So to find the length of arc ADB, we'll take 210 and we'll put that over 360 degrees in a circle. We have to multiply that now by the radius, which is given by 2 times pi times the radius. And the radius in this case is given as 18. Now, I took a step just to show you how we use that formula. Now, here's how I would actually write it out to simplify it. I would just write this out all in the numerator. 210 times 2 times pi times 18. Now, my pi got a little sloppy there, but you get the idea. And that's all over 360. Now, you could reach for a calculator, but since we want this in terms of pi, we just need to simplify what's here. And one way to go through and simplify this is by understanding some common divisibility rules. 210 and 360 are both divisible by 10, so we would divide them by 10. That leaves us 21 and 36. Now, 2 divides into 36 18 times. So the 2 divides out, and 2 goes into 36 18 times. Now these 18s can divide each other out and leave 1, so they're canceled. So what we're left with here is, in the numerator, 21 pi. In the denominator, we have 1. 21 pi divided by 21 is 21 pi. So the length of arc ADB in terms of pi is 21 pi. And of course, if we multiply that by 3.14, that would give us around 64 or so.